So thank you very much for checking in back after lunch break. If some of you happen to pass out during my talk because you just had lunch, no worries. And 5 minutes later, I'm going to talk about a different topic so you can come back easily. So the overall topic is learning theory, and I'm going to talk about the probabilistic perspective because that's the only perspective I really do understand. And there's a certain beauty in the probabilistic perspective is you usually always know what you want, right? You can write it down, it looks really beautiful in math, and you can do the math like in 5 minutes and then you're done, and you realize you can't compute what you want. Yeah? So you know what you want, it's there, it's in front of you, but you have no chance of ever getting there. So a lot of the probabilistic learning, probabilistic machine learning Bayesian statistics is about getting as close as we can possibly get in like human lifespan in a way. And I want to highlight just certain kinds of perspective in that area with a focus on probabilistic learning, but I hope the ideas generalize a bit beyond that. So the first topic I want to talk about is inference in high-dimensional spaces. And so first of all, we can clarify what high-dimensional means. And I mean, there are various different definitions of it. First of all, what kind of space are we talking about? Is it about the input dimensions or the output dimensions, the amount of data, for example, or the amount of like support points we're having in our features? So there are lots of ways, lots of dimensions in which we can be high or low dimensional. And then, of course, depending on the field, 200, 250 observations may be high dimensional because it took us 10 years to get there. And in some other fields, we have millions or even more observations, and that's then perhaps like low dimensional still, right? So high dimensional spaces are different in different fields and different contexts. And whatever high dimensional is for you in a non-probabilistic perspective, you can go to the probabilistic perspective and suddenly high dimensional is way lower because we have problems computing stuff. Yeah? So when we're trying to scale up probabilistic modeling to high dimensional spaces, we usually have to work even harder to get there and have to like make more compromises than we would usually wanted to do. For example, one topic here I want to talk about is how can we bridge the gap between learning regimes in the context of high-dimensional spaces. What I mean by that, for example, we have these kind of layered architectures of neural networks. We know they're doing really well in lots of contexts, but they usually need a lot of data depending on how flexible they are. Or we have like Gaussian processes or other kernel methods. We know there's lots of nice stuff of it. There are certain kinds of analytic things we can do. We have nice, more or less automatic uncertainty quantification in them. There are kernel methods, so they come with certain kinds of advantages. If you just have to know the kernel, then you know everything in a way. But they also come with a lot of disadvantages in terms of scaling to, for example, the number of feature support points we're having where exact Gaussian processes scale really badly. If you look at, as another example, if you look at basis function approximations such as splines or something, they scale much better to the number of feature values, like x values we're having, but they won't scale so well with the dimensionality of your input. Because when we're taking the product of individual bases over dimensions, then we have like some exponential increase in the basis functions we need. And so there's no free lunch in that way. Yeah, and as you notice, even here at ELLIS events, there's no free lunch. Coffee is free, everything, like lunch is not. Free dinner, there's free dinner. I heard there was like nice Indian food or something. So there's free dinner, but there's no free lunch. So we always have to, kind of suffer from some curse. And if we want to get certain benefits, we're getting a curse with it. If we want the benefits of kernel methods, we have to get the curse of certain kind of bad scaling. We want the nice things of basis function approximations, we get some other curse, some other bad scaling. But what if we could exchange one curse for the other? So getting the advantage of a Gaussian process and getting the curse of basis function approximation. So bridging the gap between learning regimes. And so in one study that we have done, where I just borrowed that picture from, we actually used kernel reproducing Hilbert spaces to approximate Gaussian processes, exact Gaussian processes with certain kinds of basis function approximations, while retaining nice properties of the Gaussian process, but getting the curses and also favorable scaling of certain kinds of basis function approximations. So that always comes with some kind of friction, so there's some stuff lost in it. We need some certain kind of diagnostics to figure out how those things work. But more generally, the idea is all of these methods do certain kinds of things well, certain kinds not so well, and how can we bridge the gap to actually improve our overall inference and choose the methods that are right for a specific task. Okay, so for those of you who have like passed out the next 5 minutes, next topic, you can wake up again. Another thought that is present a lot in our research, specifically in probabilistic context, is global versus local regularization, or regularization more general. So for people who are used to probabilistic learning based on statistics, regularization is just prior specification. For everybody else is regularization, but they're really one and the same. And the question that I want to discuss here is how global is local regularization, specifically in high-dimensional spaces. First of all, what I mean by that. So suppose we have, I don't know, 50 observations or something, so a genetic association study, every observation is a person, and historically getting their genome encoded was like really cumbersome, so we had 50 and that was big data, but we had like, I don't know, thousands of potential gene regions. So it's high dimensional in terms of the input, for example. And we could now go ahead and locally regularize every coefficient belonging to every gene candidate area in a way. There would be thousands of parameters on 50 observations, so it's kind of a problem. So we could go ahead and locally regularize every coefficient by, let's say, like an L2 norm or like normal prior distribution equivalently, giving some like fixed mean, fixed standard deviation, some fixed scaling in a way. And that would be perhaps locally reasonable in terms of what it regularizes. It cuts off the extremely unlikely values that those coefficients will never have. However, if we combine them, like to see what kind of predictions those prior assumptions, those local regularization would imply jointly or globally, we would see the global predictions of that would be really, really awful. So the picture here, what we see on the x-axis is R squared, so basically how much percentage of variance our model explains. So when R squared is 1, like we're explaining 100% of the variance, which in studies involving humans we never reach because there's so much noise. In physics we may be getting there, but like not in a lot of stuff involving humans or animals. So when a priori, before seeing any data, our model thinks that a priori it will explain like almost every variance there is, the potential of overfitting on sparse data is really, really, really high. So just having local regularization of each individual parameter won't do the trick if we have lots of parameters, if we just munch them together within one big thing. So what we are working in our group is how we can put the global and the local regularization together. So have global regularization that jointly controls how much complexity the model as a whole can have, for example, in terms of the a priori explained variance here, R square, while at the same time having reasonable local regularization. We could have a nice global one if our local regularization would just shrink everything to almost zero, so that globally it would be fine, but then it would be locally too informative. Conversely, if it's locally well enough, weakly informative, if you will, then globally it will just explode. So we're working on regularizers or prior distributions that are able to combine these global local regularizations to have the best of both worlds and really give sensible regularization, sensible prior informations to our models. And as kind of Bayesian statisticians, probabilistic machine learners, we are addicted to uncertainty. So we're kind of just seeing uncertainty everywhere, and if for anything, we're having the moral high ground. So whenever someone has a really complicated model and they're getting prediction, we can say, yeah, but what about uncertainty? Right? We can always make that point very easily without saying that it's really difficult to actually obtain a proper amount of uncertainty in lots of cases. And apparently we were recently bored with just having uncertainty. So we are now having uncertainty of uncertainty. And depending on where our second uncertainty comes from, we have uncertainty of uncertainty of uncertainty. Whether that's useful, I don't know. I hope it helps publishing Marvin 3 papers for his PhD. Let's see how that goes. Yeah? I'm calling that meta-uncertainty just because it sounds fancy and I was inspired by Facebook, apparently. All right, and so more concretely, the question we can ask here is how can we combine Bayesian and fragmentist uncertainty? So with Bayesian uncertainty, I mean the epistemic uncertainty I have just based on looking at a specific data set as a specific question without having to consider like a potential world of different data sets, right? So I'm just having this data set and just having my prior knowledge, what is the probability that it will rain tomorrow, right? I don't have to consider different days and or like how I would compare to different days. It's just about what's the probability that it will rain tomorrow given my current knowledge and data. Then, of course, there are like other uncertainties, like what I call here fragmentist uncertainties, which means had I obtained different data, my results would have been looking differently, right? And had I seen kind of other information from the weather stations, my forecast would have been different. And so these are different kinds of uncertainties. They have some overlaps, but like we can combine them, or we can try to combine them. In some ways, it's automatic, but there are certain places where it is not. So suppose you are doing some kind of model comparison. So you're in physics, and you're having different kinds of substantive models of your area of research, and you have reasonable belief that one of the models is actually true to some level of degree. And then you can like gather some data, and you can do model comparison to see which of the models is more likely to be true. So the outcome is a probability vector of which model is true in a way. Let's say one model is 90%, the other one is 10% true, with 10% probability true for that given data. And that's kind of some kind of Bayesian uncertainty, we could say. But what if we had observed different data? Perhaps it wouldn't be 90-10, it would be 85-15. Okay, that's close enough, I can believe in that. But what if I had observed different data, and it wouldn't be 90-10, but it would be 10-90? Would I still trust my 90-10 from earlier? Because if I had obtained different data from the same true but unknown data generating process, I would have gotten a completely different result. So idea is to combine these kind of different uncertainties to like make our model comparison and make our models more informative, and also make our decisions based on them more informed by all possible uncertainty that we could think about in a given context. That's really computational demanding, and so we need lots of simulations for it. You know, we would like to suffer for getting some nice probabilistic outcomes. A minor topic of mine, which is actually quite relevant in the context of probabilistic machine learning, is efficient cross-validation. So in kind of all kinds of machine learning, we need cross-validation to see how our model performs out of sample, because in sample we cannot trust for the danger of overfitting. So we need to do some cross-validation to repeatedly fit our model to different subsets of the data and then evaluate it on different kind of validation test sets. The problem is, if something like an optimization-based model takes you, let's say, a second to fit, and you do it 100 times for cross-validation, okay, it's 100 seconds, that's fine. But suppose that single model in a probabilistic sense wouldn't take you 1 second, it would take you a minute, or it would take you an hour. Then suddenly having to fit thousands or hundreds of these models becomes really, really painful. So generally, whatever you do, if you make it probabilistic and you want to do it properly, you are just adding 1 or 2 orders of magnitude of computation time. So if we want to do cross-validation in probabilistic models, we have to do something clever, hopefully clever, to reduce the computational burden, to in general reduce the amount of number of refits we have to do without having actually sacrificing the quality of our cross-validation procedures. So I just added this example here to show whenever you're doing probabilistic machine learning and you're really taking that probabilistic serious, you have to do a lot of shortcuts, a lot of approximation, lots of ways to still roughly get where you want, while still having the moral high ground of having included uncertainty somehow. Okay, so we do that in our ivory tower, but in the end, we want people to benefit from that. So we have learned a lot about how we learn, but how can we help users or analysts in science and in industrial areas learn from their data, right? So in an ideal setting, people would come to us, they have a research question, they have some data so that we don't have to gather it ourselves, and they're asking for our help to build a probabilistic or otherwise model. But the problem is that the amount of people who can do that machine learning, statistics, expertise, and can actually help other people analyze the data is like way smaller than the amount of people who are having data in need of analyzing. And so what we're trying to do is basically replace ourselves by a machine who can virtually sit next to the user and help them to do the proper modeling. So, for example, the analyst or the user would make a modeling choice. From that perspective, we would just do the model estimation, which is really painful in probabilistic learning, but eventually we would get there. And then the user would get out some results, which, if they're lacking the statistical or machine learning expertise, they didn't necessarily know how to work with that. So what we do, we make machines that evaluate those models, and also based on the evaluation make modeling recommendations, what to improve, what to add, what to change, to run it longer for convergence, to add more prior information, stuff like that, and to convey those evaluation and recommendations to the user. But importantly, not forcing the user to use the decision of the machine, but rather just the user decides on their own, but we are just helping them making recommendations. And the good thing is the machine doesn't get annoyed if the analyst chooses to ignore the recommendation. I usually get annoyed at some point, so in which case it's safer for the user. But of course, still we get feedback to the machine to actually learn what the user wants or needs. So that's one project with Maximilian, one of my PhD students here. And we hope that in a couple of years we have a sensible recommender system that can help in certain kind of areas of data analysis and help users actually following a Bayesian workflow for data analysis. So the kind of last topic I want to talk about today, which is really exciting, which I've stumbled upon when a close colleague of mine, Stefan Radev, introduced me to it before the pandemic, start of 2020. 2020, was the following situation. So what we're usually in when we are fitting any kind of model is we have to refit our model for every new training data that comes in. So you're training your neural network on one data, and if you have different data or there's something off, you need to refit that model, retrain it from the start, which is, I think, is something that was also mentioned in one of the previous talks. So the approximation loop, like where we're actually training our model, could be anything kind of, you can think of a neural network, but it doesn't have to be, is within the inference phase. So whenever we're having training data, we're having to rerun the whole approximation loop, running stochastic gradient descent repeatedly until convergence if there's new training data coming in. The same process will reappear, which is really computationally demanding. But what if there was a way to break out of that standard inference setting where the training is inside the inference case where we're doing inference for our training data? And some kind of answer is amortized inference. And what that does is basically it breaks apart the approximation loop and the inference phase. That is, in the approximation loop, we are learning from simulated data. We are learning the mapping from our data to whatever we're interested in a probabilistic setting, our posterior distribution of the parameters given the data. We learn that from simulations. And at inference time, that is when training data comes in, we're getting inference like this. You can think of you having a complicated neural network, and you get new training data, done like this. Yeah? That's the ideal. And it actually works, in certain cases, it works surprisingly well. So we trained the model on a quite long-lasting training force and simulated data, but when there's new data coming in, we're just getting our inference almost in an instant, which, for example, would make Bayesian cross-validation trivial. We could just have, 100 models on different training data, we would just get all the inference for all the models in a second. So this is already really successfully applied in the past couple of years on simulation-based Bayesian inference, where the only way we can access our data-generating processes through simulations. This is a place where amortized inference has already just humiliated the state of the art. that has been there for decades, basically. And we now see how far we can scale it. How high dimensional can it be? We can now handle 50 dimensional quite well. Previously, we couldn't even handle 5 in certain cases. Now we can handle 50 or more, but the question is how big can our substantive models of interest, physical, psychological or similar, be to really be usable in an amortized framework where we first train on simulated data and that get inference almost instantly. I don't have an answer for that, but I intend to write a lot of grant proposals on that and get a lot of funding. So let's see how that goes. Thank you so much for listening to my talk.
Thank you very much, Paul. Questions? So maybe I start with a question. You mentioned on one of the slides that you kind of combine Bayesian and just uncertainty. The first idea which immediately popped up into my mind was the idea that you show something like with high probability Bayesian uncertainty is, let's say, delta approximately correct. What's delta? Is that what you have in mind, or is it going into a different direction?
I'm not sure if I understand the question. I wouldn't speak of what's the correct uncertainty of these, because they are living in different domains. So both of them are correct to a certain degree, but they're measuring something different. They're measuring something different about the world. And if I can combine that, I know the uncertainty in various dimensions of uncertainty of variation in the world. I'm not trying to improve one by the other, necessarily, if that was the question.
Yeah, well, this was one way of it.
Okay.
I think you answered my question.
Okay, that's good.
Further questions? This is always the problem with these logarithmic-oriented talks. I could ask. Here we go.
So I'm repeating the question because it wasn't without microphone for the recording, and also to make sure I understood correctly. So you're saying basically the question is, during inference phase, do I need to readapt to the new situation? No. So think about, we have a physical system that I have reasonable belief that it's true to some degree of reality. And so I can, let's say that system is a stochastic differential equation, I can simulate from that system. The inverse, like inverting the stochastic differential equation would be really difficult, but I can simulate from it. So I'm training, in this case, a neural network approximator on that simulated data. I'm learning the probabilistic mapping between the data and the posterior distribution that contains my uncertainty. And that makes it amortized in a way that whatever data I'm now putting in that is compatible with the structure of the model, I will immediately get the posterior distribution that the neural approximator has learned. So by the time I'm having real data, assuming the model is true, I can just feed the data into my, invert basically in an invertible neural network to get my learned posterior distribution for that data. That said, if my real data was somehow coming from a different process than my simulation from, where I have model misspecification, some simulation gaps, first of all, we would have to detect them. We can now do so. And the second one is we have to adjust somehow, which may be requiring some kind of retraining, but that's something we're investigating. How did what? So the question is, how do we detect if the real data is different from the data generating process? So think about the neural network architecture that does that mapping from data to posterior. Consists of two networks. The first is a summary network that compresses the data into sufficient summary statistics that are specific to the model, that are learned, but they're model specific, and that contain all the relevant information. So in statistics, we have this idea of sufficient statistics, or ideally minimal sufficient statistics, that contain everything the model can learn or needs to know from the from the data. And this is something the first network learns, kind of some sufficient summary statistics. The second one is an invertible neural network that basically has some easy space on one end, some like multivariate Gaussian, and the complicated space, our posterior distribution on the other hand, and I can just freely go in both directions because it's invertible. And so the summary network puts gives us these summary statistics. And if we put some kind of structure on that latent space, let's say it's again multivariate normal, could be different, then we can check how our real data looks in that latent summary space. And that latent summary space was learned from simulated data, so only under the simulated data is it multivariate Gaussian. If my real data is outside of that set, I have some reasonable evidence that there is some problem.
Okay, further questions? If this is not the case, let's thank the speaker again.
Thank you.